In this lesson, we're going to introduce the idea of vectors in a plane, and also we'll look at some vectors that are three-dimensional vectors in space. So while we have some quantities that can be measured with just a single number, like I have $5, or I can run 10 miles per hour. I don't know if I can or not, but anyways, probably not. And so those are just single numbers, but some quantities require two numbers, like force. Force has a magnitude and a direction, all right? So in order to define those, we have vectors, okay? So a vector has two quantities, and those quantities are magnitude and direction, all right? So let's see how to describe these vectors. So a quantity that can be described with a single number is called a scalar. So a scalar are just numbers like 2, 5, -7, pi, so on and so forth. Okay, these are scalars. But a vector has magnitude and direction. All right, so it has to have two quantities that are specific to it. So we can write a vector. When we write a vector, we'll write it something like 5, 2, and we're going to put it in these little pointy parentheses here, all right? Graphically, we can show it as a directed line segment. Now, this looks like a ray. In geometry, we draw rays, which mean they go on forever because it has an arrow. But this doesn't go on forever. It starts at P, goes to Q, and the arrow tells us the direction it's going, all right? This is a graphical vector here, and it has some quantities. It has a length. So geometrically, it has a length. And so the length is going to represent the magnitude, all right? When we put this in the coordinate plane, we can either start it at 0, 0 and go to 5, 2, and that would be the vector here, 5, 2 is what we would say here, all right? So this is the vector 5, 2. All right, so this is the vector 5, 2. Get these squared away here. Okay. All right. Or we could start somewhere else. This vector right here is also 5, 2. So these are what we call equivalent vectors. All right. So this vector here is in standard position. And this one down below is not in standard position. But they both have an initial point and a terminal point, okay? So terminal point, okay? So they start at one place and they go to another. And so 5, 2 represents the horizontal and vertical components of these, all right? So this is what we call the component form, what I've been writing there. And the component form of a vector, this vector above, is written as 5, 2. Okay. Now, notice a couple things here. Let's back up here. All right. I've skipped over a couple things. So this vector that goes from 0, 0 to 5, 2 is written as PQ. Okay, so we can name a vector like this. Now notice that symbol over above is not a ray symbol. If this was a ray that went on forever, we'd say this, all right? And so technically this is not that. Notice the arrow has one little hook on it. We call it a harpoon is the name of that symbol, okay? So that would be the PQ, all right? That would be the name of it. And we can describe the magnitude of PQ, the length of PQ, with these absolute value bars. Or sometimes you'll see it written like this, PQ with 2 bars there. So it could be written both ways. All right? So that means the magnitude, which, as we said, is the length. Okay? All right. Well, component form, again, is written as 5, 2, which describes the horizontal and vertical directions, okay? So the component form of a standard position vector with terminal point v1, v2 is written like this, with these little pointy brackets on the end, okay? So with that in mind, let's go ahead and graph a few vectors, okay? Now notice also, see this bold and non-italics V and bold and non-italics W and R? So in print, that's how we can represent a vector. Now when you're writing these by hand, you can't really write in bold, okay? Not very easily. So sometimes we'll also write it like this. Vector W is -3, 2. And this is vector R, which is 3, -2. So we'll put that little harpoon over the top there, all right? So let's graph these here, all right? So W is the vector -3, 2. Well, that means in standard position, we would start at 0, 0, and we're going to -3, 2. We'll find that point there, and we can draw in our vector. Then the vector 3, -2, well, that's going to go right 3, down 2. And so that's going to be down here. And so that vector is this, okay? Now notice these vectors have the same length, and they're going in exact opposite directions. So we call these opposite vectors, okay? So they have the same magnitude, the same length. You can tell just by their numbers the same there, all right? And they're going in opposite directions. So, all right, now the magnitude is the length, as we said. So let's think about, well, what is that length there, all right? Well, this length here, we could use the Pythagorean theorem for, right? Going over 3 up 2, okay? So this is this magnitude of, what was this? This was W. So the magnitude of W is the square root of 3 squared plus 2 squared. Okay, just using the Pythagorean theorem there. And so that is what? 9 plus 4, which is 13. Okay? Well, give it a try. You might pause the video if you want to try it out here. And look at vector V and write what the magnitude and component form of that. Well, the component form of this, we're going to write 4 down 2. And so 4, -2. Okay. So the component form is 4, -2. The horizontal always goes first, the x direction. Okay. And the y direction is second. All right. And so the magnitude, if we use the Pythagorean theorem, all right, you could say, -2 squared plus 4 squared equals v squared, or the magnitude of v, vector V, is 4 squared plus 2 squared, square root. We don't need the negative because it gets squared away. We're just talking length. And that is 16 plus 4, which is 20. So this is the square root of 20. Remember how to simplify that? That's the square root of 4 times the square root of 5, which is 2 square root of 5. So there's the magnitude. Okay? So to summarize this stuff here, if we got a vector PQ, V equals PQ, that is, where P and Q are the initial point and the terminal point, we can find the value of that vector by subtracting the x's. That gets our horizontal movement, and subtracting the y's, all right? And you need to subtract the terminal point minus the initial point to get that, because the direction matters, positive and negative. The magnitude has just come from the absolute value, okay? And so the absolute value of V is the square root of the x distance plus the y distance squared, okay? Now, while we're talking about this, let's think about space vectors, three-dimensional vectors here. So here we have a graph. Let's see if we can get it to work here. So here we have a Desmos 3D graphing calculator, all right? And so here is a three-dimensional graph which has x and y and z coordinates. And so here we have a vector. This is the vector 2, 2, 1. It goes from the origin to 2, 2, 1, all right? So that's that vector there. Okay, we can find its. Turns out we can find its magnitude. It's pretty interesting. So this is going 2 in the x direction. It's going 2 in the y direction, and 1 in the z direction. Now, okay, so you got to think three-dimensionally here. Okay, so we're coming over, and then this one's going up. Okay, well, if we think about this here, what is the length of this vector? Well, that dotted line there that I just drew, this is going to be, since it's in this right triangle with 2 and 2, it'll be the square root of 2 squared plus 2 squared. That's 4 plus 4, so that's a square root of 8. Okay, well, so that's the square root of 8 there. So let's find the length of that vector there that's drawn in. Okay, so there's that vector. Okay, so remember this is in three-dimensional space, so you got kind of a view issue going on there. Okay, let me try drawing this a little differently real quickly here. Okay, that might help. Let's get a different view. Okay, so let's stop it. Where do you think? How about right there? So you can kind of see it in space. So we're going over 2 this way, and up 1. Okay, and we just found out that dotted line there is the square root of 8. So I've got this right triangle here. I'll draw in blue. That right triangle is the square root of 8 times 1. So this magnitude using that right triangle, so this is v, our vector v. So the magnitude of v is, actually called v1, I guess. That's what's written over here. The magnitude would be the square root of 8 squared plus 1 squared. Okay, so, well, this is just the square root of 8 is just, the square root cancels there. And where did that 8 come from? Well, that came from 2 squared plus 2 squared, right? So what's really going on? All that's really going on is we can just write this as 2 squared plus 2 squared plus 1 squared. Okay, so kind of a cool result in 3 dimensions. The Pythagorean theorem, the length of the vector is x squared plus y squared plus z squared. All right, so that's the 3-dimensional Pythagorean theorem. And what do you think would happen in 4 dimensions? Well, the same thing. You might say, well, how do we do 4 dimensions? Well, that's a little different topic for a class called linear algebra. So linear algebra deals with vectors of any dimension. So anyways, all right, so the moral story there, all right, so our 3-dimensional vector has 3 coordinates, x, y, and z. So the vector itself would be the difference in the x's and the y's and the z's, and the magnitude would be those squared, okay? So nothing new, just one more variable. All right, so vector operations. Okay, so we have a couple operations. We've got scalar multiplication. That's what we call when we take a scalar times a vector. And the way we define that is we're going to multiply the scalar times each of the components. And then we have vector addition, and that's just going to be if we add 2 vectors. If u is u1, v1, and v is v1, v2. To add 2 vectors, we're going to add their first coordinates, or their first component, and add their second component. Okay, the leftover is what we call the resultant. So let's try it out here. So if we have u at negative 2, 3, so let's graph u at negative 2, 3. So negative 2, 3, there it is. And we have v at 2, 1, and there's v at 2, 1. Okay, so v and u. We'll label those like that. And so let's go ahead and find 2u. Well, 2u, according to our definition up above, is 2 times negative 2, 3, which is negative 4, 6. So negative 4, 6 would be, let's go, -4 and 6. Okay, and so we get this vector here. Notice that this vector goes in the same direction as u, but it's twice as long. See that? We're going over 2, up 3, over 2, up 3. It's twice as long. So the magnitude is twice as long, same direction. Okay. What if we do -v? So if we do -v here, then let me grab a different color here, all right? So -v is -1, if you want, times 2 comma 1, and that would be -2, -1. So -2, -1 is over here, and so there is -v. Notice it takes it the other direction, okay? All right, and then one more here. If we wanted to add these two things here, so if we have u plus v, well, u plus v is going to be found by adding the u vector, adding the first component. That would be the -2 plus the 2. Add the second component, so we have 3 plus 1. And so that's going to be actually 0, huh? 0, 4. So 0, 4 is right up here. Okay? Now there's a special relationship between this u and this v. If we take this v, and we notice the v is right 2 and up 1. So if I move that v and slide it over to here, and I attach it to the head. Now these arrows, we say they have a head and a tail. So the head, if this was like an arrow, it would be like the arrowhead, and the tail of the vector is the end of it that doesn't have the arrow. So if we attach the head of the blue one to the end of the red one there, notice this. We've got blue plus red. We've got u plus v, and u plus v gives us the resultant r. What if we wanted to do it in the other direction? What if we wanted to take this blue one and move it over to the end of v? Well, if we move that blue one over there, then we notice we can do red vector plus blue vector takes us to the end of the endpoint 0, 4. This is what we call the parallelogram method, because notice I just made a parallelogram. So I can, if I want to show this graphically, I can draw this parallelogram by attaching the tail of one to the head of the other, and together by adding, they're going to end up where the resultant is there. And what happens when we add v plus -v? Well, we had -v here. So if we take v, which was 2 comma 1, and we add that to this -v, which was -2 comma -1. Well, what do we end up with? We end up with 2 plus -2, which is 0. 1 plus -1 is 0. 0, 0. So 0, 0 is what we call our 0 vector, okay? So we kind of skipped over that there, but our 0 vector is 0, 0. We have to have that, otherwise this whole number system of vectors doesn't work. It has no direction and no magnitude. It's just a point, kind of, okay? All right, so that's the idea there. That's how we add and multiply scalars and vectors. Couple more little things we need. One topic is sometimes we want to find a unit vector. A unit vector is a vector that has a length of 1, and it's in the same direction as the original vector. Okay, we just saw when we multiplied by a scalar that it changes the length, but it doesn't change the direction. So the unit vector has the same direction of v. So it's a unit vector in the direction of v, but it has a length of 1. And we find that by taking a vector v and dividing by its magnitude. That's the same as taking v times 1 over its magnitude. Now remember, magnitude is a scalar. So we're multiplying v, the vector, times a scalar, and that's going to give us a new vector that's going to be length 1. Okay? So let's try that for the vector -4, 5. Let's find its unit vector. Well, first we need to find the magnitude of v. And the magnitude of v would be the square root of negative 4 squared plus 5 squared. Okay, and that's going to be 16 plus 25, how about 41, right? So 16 plus 25, square root of 41 is the magnitude. So to find our unit vector, let's call u our unit vector. We're going to take 1 over that magnitude, which was the square root of 41. And we're going to multiply that times negative 4, 5. Okay, and that will give us a nice ugly numbers, negative 4 over the square root of 41. Not worried about rationalizing that, by the way. Okay, there you have it. All right, now let's verify that that has a length of 1. So there is our unit vector. Okay, and let's find its length. So I can't get that. Anyways, the magnitude of u would be the square root of negative 4 over the square root of 41 squared plus 5 over the square root of 41 squared. Well, that's going to be the square root of 16 over 41 and 25 over 41, which is the square root of 41 over 41. And 41 over 41 is 1, which is 1. All right. So we get kind of some ugly looking answers, but that's okay. We know that it has length of 1 when we divide by the magnitude. Okay. So which leads us to something called standard unit vectors. Standard unit vectors are the vectors 1, 0 and 0, 1. That's supposed to be a comma there. Let's make that a comma. Whoops. So 0, comma 1. These vectors obviously have a length of 1. Okay. So 1 comma 0. Here is our I vector. And it's going to the point 1. Okay. Our j vector is the vector that goes up 1. Okay. So j goes to the right 1. J goes up 1, I goes right 1, okay? So we can show that any vector can be written as a linear combination of these. What that means is if we have a vector, let's say we got a vector between the 2, 0 and negative 1, 3, okay? Let's find this in component form and in terms of I and j. So we have the points, let's see. 2, 0, it's going from 2, 0 to negative 1, 3. Okay, so something like this, all right? So we've got this vector going up like this, okay? And so what's going on here? Well, this is going left. Let's do our eyes in one color here, okay? So it's going left, 1, 2, 3. So that's like 3 I vectors, and they're actually opposite, so they're going negative. Okay, so we have negative 3 times 1, 0. And then we have our j vectors, which are going up 1, 2, 3. So we're going to add 3 j vectors, because a j vector is just 1 unit long. And so this is what we call a standard form, or written with standard vectors, standard unit vectors. Well, this is the same as negative 3, comma 3. All right? So the power here is this. It just kind of looks like an algebraic expression. This is kind of like coordinates. And when we work with them, here we can kind of use algebra when we use standard vectors, standard form, I should say. When we have it in component form, we got to think about things a little differently, but they mean the same thing, okay? All right, so what about direction angles? Last thing here. And so to find our direction, we just need this angle theta here. So to find this angle theta, well, we're going to see, you probably guessed it, we're going to use some trigonometry. So we're going over V1, also known as the x direction, and V2. Those are the components, all right? And so if we want to find this, we can use some trigonometry. So think about this. How can we find V in terms of V and theta? Actually, this should be the magnitude of V. Okay, so let's put some absolute values around that. Okay, so in other words, let's say we know the magnitude of V. Let's just pretend for a moment the magnitude of V is 3. And let's say we know theta in radians. Maybe that's pi over 6. So let's think about some specific numbers. What would you do here to find a V2? Well, if we know this and we know this, we could use sine, right? So we know the sine of pi over 6 equals V2 over 3. And if we multiply both sides by 3, we get V2 is 3 times sine pi over 6. And we know the sine of pi over 6 is 1/2, so this would be 3/2. Okay, and we could do the same thing for V2. We know the cosine of pi over 6 would be V2. No, V1, sorry about that. V1 over 3, something didn't seem right there. Multiply both sides by 3. 3 cosine pi over 6. We know the cosine of pi over 6 is root 3 over 2. So this is 3 root 3 over 2. So, all right, so if we know the angle, then we can find them that way. We can find them with sine and cosine like that. So this would be 3 square root of 3 over 2, comma 3/2. All right, so to generalize that, what did we just do there? Well, let's see, we did, for the first component, we made it cosine, right? So it ended up being V1 was just the magnitude of V times the cosine of the angle. And V2 is the magnitude of V times the sine of the angle. Now that should look familiar there, because this is really just an x and a y. So remember, recently, we did our polar graphing, and yeah, that's just the x and the y from conversion for the polar graphing, right? The radius times the cosine, radius times the sine. So nothing terribly new. We can write that in standard unit vectors like this. So it's the magnitude times the cosine times I plus the magnitude times the sine times j. All right. And finally, we can find that unit vector by taking v divided by the magnitude of v. All right, so let's try that out here. So let's find the magnitude and directional angle of 3, 2. Okay, so, well, the magnitude of 3, 2, let's call this v vector, all right? So the magnitude of v is the square root of 3 squared plus 2 squared. And so that's going to be the square root of 13. Now the angle, okay, actually we haven't said that, but how do we find that angle? So we're going 3, 2 up here like this. How do we find that angle? Well, tangent is the key, right? Tangent of theta is 2 over 3. So theta is inverse tangent of 2, 3, and that comes out to about 33.7, or actually 690 degrees. By the way, we'll use degrees and radians kind of back and forth. If you're writing something in degrees, make sure you put a degree symbol. If you're talking about an angle that doesn't have degrees, then it's in radians. But that makes a little more sense to us when we're talking about non-special angles. So. All right, there you have it there, okay? So we can find the angle, we can find the magnitude, okay? In space, with our three-dimensional vectors, we can do we have all the same relationships, so this is true for two-dimensional or three-dimensionals. If two vectors are equal, then their components are equal. Component form, we just subtract the x's, the y's, and the z's. Okay. The magnitude is just square each of them and add. Okay. Unit vector is the same. Vector addition is the same. Scalar multiple is the same. We just have one more component. All right. So there you have it. All right. So there's the basics of using vectors, finding angles, and component form and standard unit vector form. So I hope that gives you a good start. Thanks a lot.